Thank you very much for coming. My name is Perry Wald. This is my colleague, Tom Adamski. We are solutions architects in AWS, and we've come here today to talk to you about network fundamentals. Now, this is a level 200 session, so just a little bit of a level set here. We're talking about a basic level of networking. We're looking at talking about networking from IP networks, addresses, routing, how to build a VPC. If you are familiar with networking but have never used AWS, or familiar with AWS but never done networking in AWS, this is the level you want. If you've already done a lot of deployment inside AWS, then this is probably a little bit basic for you. So let's get started. There's the internet, and there's AWS. And people tend to use AWS as if it were a kind of data center, a virtual data center. As a result, they deploy things into that data, the same kind of stuff as you deploy into your data center on premise. They might be EC2 instances, that's hosts. They might be databases. They might be EMR clusters, that's analytics clusters. Those things need to live somewhere in a data center, and they typically need to talk to the internet. So for that, we have something called a VPC. Now, when you get an account, you get a default VPC. And that default VPC gives you a lot of the things that you need to build your networking in AWS. It gives you IP ranges, something called a CIDR range. We're going to talk about that. It gives you subnets and availability zones for resilience. We'll touch on that. It gives you routers to be able to route out to the internet, because that's quite useful. And it gives you things like security groups and network access lists. I'm going to refer to them as Knackles, to be able to provide security. Now, the default VPC is a good starting place for when you start with AWS, but what we're going to spend the first 15, 20 minutes talking about is how you build all those components in the VPC yourself, and then we're going to hand over to Tom to talk about some of the more complex components that come up with networking. So, with that in mind, I'm going to talk about IP addressing. I'm going to talk about creating subnets, routing, and putting some security around it. Let's start with IP addressing. So this address, 172.31.00/16, this is what you start with in your network, in your default VPC. And let's just look at that a second. That's a useful address. I didn't just randomly choose that. It splits into two halves. 172.31 describes the network half, and 0.0 describes the host, the actual system on the network. 172.31 comes from a range called the RFC 1918 range. I'm going to pass over a lot of these things. I'm not going to go into too much detail, but these are all available to look on the internet. The RFC 1918 range doesn't exist anywhere on the internet. It's a private IP range, which means that if you use it in your VPC, you're not going to conflict with anything on the internet. And that's quite important, because if you conflict with something on the internet, you can't talk to that thing. Now, conflicting is also important on-premise. So if you're connecting to on-premise, you're connecting to other VPCs within AWS, then you need to not be using the same address everywhere. You need to be using a different set of CIDR ranges for each VPC so that you don't overlap. And that's going to be quite important, because overlapping addresses can't talk to each other easily. So just to touch on that /16, that /16 really means 65,000 odd addresses. That's a great place to start. Lots of space for you to expand and grow what you're running in AWS. But if you run within a business that has a networking department, it's quite normal that they may ask you to use a smaller range. So when choosing the range, when choosing the size of the network, have a think about how big, how many systems you're going to run in that environment, and choose the subnet accordingly. So that was a CIDR range. That's a range of addresses you're going to use inside the network. But what do you do with those? Well, let's start again with that VPC, that virtual data center, as I've talked about it, in the cloud. That has the CIDR range, and we want to break that up into availability zones. Now, an availability zone, in this case, I've highlighted Dublin's 3 availability zones. Availability zones are separate risk domains. Each of them are 1 or more data centers. Those data centers are on different power grids. They have different flood profiles. We do this so that if something were to affect an availability zone, it wouldn't affect multiple availability zones. That's really good for resilience. But in those availability zones, you need to put subnets so that you can talk one to another. The subnets, in this case, are subdivisions of that CIDR range. In this case, 172.31.0.1 and .2 dot something /24. In this case, I'm using the first 3 numbers of the IP address to denote the actual network, and I'm using the last number to denote the machine. And in this case, each subnet can contain about 250 addresses. Now, I mentioned all of these IP things, and these are all IPv4. I'm going to brush fairly quickly over IPv6, but basically, we're running out of addresses. So IPv6 came along, which has many more addresses. It comes from a group big enough for everyone to have a unique address, but those addresses don't exist on their own. In AWS, we run something called a dual stack, which means those addresses are overlaid on top of the same instances that your IPv4 addresses are. So if you start to use IPv6, every network and every instance will have both an IPv4 and an IPv6 address. Great, so that's a lot about addressing, but now we're going to talk about talking between addresses. None of this is about security yet, that will come later. To talk between addresses, we need to be able to route. And a routing, or a route table, is a set of rules that tells us how to move packets around, where to put the next packet. Now, every default VPC has a default route table, and that default route table simply says, everything in my CIDR range is inside my VPC. But you can assign different route tables to different subnets, and we're going to look at how to do that in a minute. But before we do that, let's just have a look at where you configure route tables. On VPCs, you go to the route table tag, and you hit, my clicker is not working, you hit the route table tab, and you will get a routes table. And as it shows up there, 172.31.0.0/16 is local. That means anything in my CIDR range in any of the AZs will talk to one another. But what about the internet? We said right at the beginning of this that it's really useful to talk to the internet. So the easiest way to work through this is to do some examples. We start with your virtual data center, your VPC, and the internet. Now, there are 3 things that you need in order to communicate with the internet. You need to have some form of connection to the internet, you need to have a route to the internet, and you need to have a public address. And if you recall, I said that 172.31 was a private address. It doesn't exist on the internet. So in this case, we create a subnet inside that VPC, and we say that that subnet is a public subnet. Now, public subnet merely means when I launch an instance, that instance, as well as getting its private IP address, it gets a public IP address. In this case, 198.51.something. Now, that's great. That deals with number 1, a public IP address. Number 2, I need a connection to the internet. So what I do is I create an IGW, an internet gateway, and I connect that to my VPC. Now I have a connection. That's 2 out of 3, not bad. The third thing I need is a route. And in this case, the 000/0, that means default route. That is telling anything in my subnet that the default way of getting out of the subnet, the way to get out to any address that isn't inside the subnet, is via the IGW. Now that creates something called both inbound and outbound internet access. What I've done is I've created a construct where my 198.51 address can talk to anything on the internet, and anything on the internet can talk to that 198.51 address. We will put security in later on. In this case, it's a very typical setup for a web server. But another common setup that people want to use is if I want to go out to the internet, maybe for a patch update, maybe for an API call, but I don't want the internet to get back to my systems by default. Well, in that case, I create another subnet, but I denote this one as a private subnet, not a public subnet. Private subnet just means stick with the private range, don't give me a public address as well. Well, that means I need something to give me access to the internet. And in this case, the thing that gives me access to the internet is a service called Gateway. Gateway is a one-way valve. It allows systems inside AWS, inside your VPC, to get out to the internet, but it only allows responses to requests that have come from inside. If a request comes from the internet and tries to get through the NAT gateway, it will get rejected. The NAT gateway is a one-way valve that only allows responses to requests from inside. And in this case, I add a default route, 000, but I point it towards my NAT gateway. I don't point it towards my internet gateway. This creates something called outbound internet access. Systems can get out, hosts, instances can get out to the internet, but the internet can only respond to requests. Now, so far, in a very short space of time, we've talked about IP addresses, we've talked about routing, and we've talked about internet and NAT gateways, but we haven't talked about security. So we're going to talk about security next, and I'm going to cover 3 items. I'm going to cover security groups, network access control lists, Knackles, and I'm going to cover flow logs. So let's start, let's start with security groups. Now, security groups are AWS's distributed firewall. And the most important thing to know about a distributed firewall, or in fact, most firewalls, is that they are what's called stateful. That means that a request that comes from one direction automatically sets up permissions for the response to that request from the other direction. And that saves you a lot of trouble because it saves you having to set up a set of rules for inbound and outbound access. So let's just look at what firewalls do, what security groups do. We'll start with our VPC, and we'll start with seven instances inside that VPC. I'm going to choose that 4 of those instances are web servers, and stuff on the internet wants to talk to those web servers. And 3 of those instances are back-end servers, and the web servers want to talk to the back-end servers. So let's put them in some logical groups. In this case, I'm going to put them in a My Web Servers group, that's the top one, and I'm going to put them in a My Backends group, that's the bottom one. Now let's lay some rules over these. For the My Web Servers group, I want a rule that says allow web traffic from anywhere. That's sort of a sensible thing for a web server. But for the backend group, I want a rule that says only allow communication from my web servers. I don't want anything else to talk to those back-end servers. That's security groups. Let's look at how you configure them. Well, you go into security groups on the VPC environment, and you create them. And in this case, I created an inbound rule that says port 80, HTTP, web traffic is allowed from anywhere. And I've assigned that to the My Web Servers group. For the My Backends group, I have a rule that says traffic is allowed from the My Web Servers group. And in fact, if you look, I don't give IP addresses, I give a specific security group ID, and that ID matches the ID of the My Web Servers group. This is a really important feature of security groups, especially when you start scaling servers up and down. You don't have to worry about IP addresses of the servers. If the servers live in the security group, then you refer to the security group, and that is the decision that we make about firewalling. Now, that didn't move forwards. Now, I've talked about security groups, and I'm going to touch on Knackles. Why I say I'm going to touch on Knackles is because really what I want to do is I want to highlight the difference between a security group and a Knackle. Security groups are stateful, and they're really firewalls. Knackles are just network control lists. They really should be used only for very coarse-grained decisions, like I don't want any traffic from that network, or I only want to allow traffic from this particular IP range. And most importantly, they're stateless. Just because you've allowed traffic in one direction doesn't mean that the traffic in the other direction is permitted. In fact, if you don't explicitly allow things in both directions, you're going to start getting into difficulties. Knackles should be relatively short. If you start finding that you've built Knackles with long, complex sets of rules around ports and IP addresses, you've probably started configuring security groups instead, but we're using Knackles. So please, please, Knackles are coarse-grained controls, and they only work around the edges of networks. Now, we've talked about the tools for creating security, for controlling flow of data, but we haven't talked about how you look at it, and that's flow logs. Flow logs work at a VPC level, at a subnet level, or at an instance level. I can inspect any of those three items, or all of them, and I write my output to either an S3 bucket or a CloudWatch log. It's really useful for providing visibility into what's going on my network, troubleshooting if I've set up the wrong rule, or analyzing traffic flows. And I stress analyzing traffic flows because flow logs do not contain the payload's data of your packets. They only contain the description about the packets, the addressing, etc., the metadata, and we're going to look at that in a minute. But just before we look at that, let's look at how we configure them. We go to our VPC, we click on the flow logs tab, we create a flow log, and we say whether the destination is S3 or CloudWatch. It really is that simple. Now, what does a flow log look like? Well, for anybody who's ever done network troubleshooting, it's a page of numbers. But what I'm going to do is I'm going to dive down into one of those, and we're just going to translate it into English. Now, I have blurred out a section because that came from my account. Every flow log also contains the account that the traffic was seen on, and that's quite useful if you've got many accounts. In this case, the flow log tells me the network interface that the data was seen on, the source IP address and the source port. This is a public IP address in this case, and it's coming from a high number port. So I know that this is from public address 210 blah, blah, blah. It has the destination IP address and port. In this case, the destination IP address is inside my VPC, and it's port 22, which is SSH. It has the number of bytes that was, and it tells me whether that was an accept or reject. Now, that gives me almost my entire sentence, but I have to work one bit out. I work out that if it's destined for SSH inside my VPC, then this was inbound data from the public internet to SSH. That's really useful. If I'm not working, I can put a flow log on and see why traffic is being blocked. Now, I very, very quickly talked about all of the components that go into building a default VPC, and I'd strongly encourage you to play with a default VPC, but then to set this up yourself, because when you set it up yourself, you get to choose what all of the variables should be. I haven't mentioned DNS, and in the last minute I'm going to mention DNS. Inside AWS, we provide you with DNS services as well. Those services are switched on by default, although you can switch them off, and they provide two things. They provide DNS resolution so that your instances inside a VPC can resolve public addresses and addresses of other things in the VPC. And they also include the ability for us to assign DNS names to the instances so you don't have to just use IP addresses. Now, that's really worth considering and looking at, but I'm not going to go into more detail here. I'm just going to say that if you're interested in DNS and not having to manage all of your own DNS, it's worth considering looking at Route 53. With that, I'd like to pass over to Tom, who's going to talk about some of the higher level services.
Thank you, Perry. Hey, everyone. All right. So Perry has taken you through setting up your first VPC, connecting it to the internet, and securing it. And I'm going to go through how you can connect multiple VPCs on AWS and how can you connect your VPCs back to your on-premise environment. So we'll start off with the options we have to connect VPCs in your AWS environment, in the cloud. And we'll look at two options. We'll look at VPC peering, and we'll look at TransGateway. Well, let's start with VPC peering. So Perry earlier compared the VPC to the equivalent of your data center on-premise, but running in the cloud. So VPC peering in that context would be like a piece of fiber or like a leased line between those data centers. So if you have two VPCs you want to connect, you can establish a peering between them, and it can start communicating with each other. If you have another VPC that you need to connect to that environment, you can create another peering, and now the VPC in the middle can talk with both edge VPCs. However, one thing to remember here is VPC peering is a one-to-one relationship. So you can't have this path happening. You can't have traffic traversing a VPC to get to another VPC. So if you have a requirement for those edge VPCs to be able to talk to one another, you'll need to set up your own VPC peering here and establish a connection between them. So let's add a fourth VPC to the mix, and if we want to have any-to-any communication, we'll need to add additional peerings in here to have that happen. So all of the communication is happening privately, and the VPCs you're connecting over peering can be in different accounts, and they can even be in different AWS regions. So you can connect a VPC in Ireland with a VPC in US. Finally, when you're connecting VPCs to each other over peering, you need to make sure that you don't overlap any of the CIDR ranges you decided to use for your VPCs. From a setup point of view, establishing a VPC connection is very much a decentralized process. So the owner of each VPC is making a decision to establish that peering with the owner of the other VPC. So in this case, the owner of the VPC on the left is going to send a peering request to the owner of the VPC on the right, and then the owner on the VPC of the right will accept that request, and the peering is established. Very simple. The final step is to update the routing tables on each side to make sure the traffic can flow. So if we zoom into the VPC on the left, we now see an additional routing entry in the routing table that's telling us how to reach the IP address range of the VPC on the right, and the destination is going to be the peering connection we've just created. So last year, we've announced the availability of another option for connecting your VPCs together, and that's the TransGateway. So if we go back to the world before the TransGateway, we can see our peering mesh again. And it's fine if you have just a few VPCs, but once you start getting into 10s, 12, 13, 20 VPCs, they need to connect to each other. It's becoming very complicated to manage. Plus, you will likely hit the limit of the VPC peerings a VPC can have. That's 125. So how does TransGateway help us? So TransGateway is a distributed, managed routing service that you deploy into a region, and you can connect and attach VPCs in that same region to your TransGateway, and then allow for any-to-any communication from a routing point of view, or you can isolate some VPCs to allow them only to talk to each other. So if we now add some routing information here, and we assume that all our VPCs are in the 172.16 block, how is our routing going to look like inside our VPC? So if we zoom into that routing table, we now see a different entry that's pointing to any addresses in the 172 block and saying that those addresses are now reachable via the TransGateway. So rather than having a single entry per peering like we had before, we can now have a single entry sending all the traffic to the TransGateway, and then the TransGateway actually has its own routing table with specific information about every single attachment it has, including the VPC that we're sending traffic from. So communication, similar to peering, is happening completely privately. Your TransGateway and your VPCs can be in different AWS accounts. However, the TransGateway and the VPCs have to be in the same region. We've announced end of last year that we are planning for this year to make connectivity between transit gateways in different regions available, but that's coming. Okay, so if you're comparing the two and making a decision which one to pick, which technology to pick, VPC peering or TransGateway, here's some ideas. You can look at some comparison numbers that you can look at. But in the end, it's going to come down to the number of connections you can have and how easy it is to manage that environment. So if you're configuring more than 10, 15 VPCs, TransGateway is probably something you want to look at. Okay, so we've connected our VPCs on AWS. Let's start connecting them back to on-premise. So we'll go through a scenario where we have our on-premise environment on the left, and we will have our VPC on the right. And we'll look at two connectivity options. We have AWS site-to-site VPN. That's effectively an IPsec VPN tunnel, typically running over the internet, connecting your VPC to on-premise. And the other option is AWS Direct Connect. That's a dedicated physical connectivity into the AWS backbone. So VPN is often the starting point for many customers. It's an easy thing to set up, and you can do it with not a lot of effort. So to set up your first VPN, first of all, you need to define the customer gateway, and this is going to be the on-premise end of your VPN connection. And this could be your router, your firewall, anything you manage on-premise that supports IPsec. On the VPC side, you'll create another gateway, a virtual private gateway that you associate to your VPC, and that will be the other side of your VPN connection. So once you have those two endpoints, you can create your first tunnel, you can create your first connection, and each VPN connection actually consists out of two separate IPsec tunnels. And the reason why there's two separate tunnels is because we give you two separate VPN termination endpoints in different availability zones for high availability. Finally, if you're not using a dynamic routing protocol, like BGP, for example, you would have to update the routing table inside the VPC to tell it how to reach the on-premise range. So VPN is great, but because it often runs over the internet, you might sometimes have some unpredictable experience. So if you want more predictable and consistent experience for your connectivity to AWS, that's where you would look at AWS Direct Connect. And here, first of all, we're going to zoom out a little bit from our VPC and look at the larger AWS cloud. And then inside, we have our VPC we created earlier. But outside of that VPC, that private environment, we have other services. These services are managed services that live on the AWS public address space. These are things like S3, DynamoDB, CloudWatch for monitoring. All those services are outside of your VPC. And now we want to use Direct Connect to connect from our on-premise environment both to our private VPC, but also to some of those services that are on the public address space. To do that, we would use one of our Direct Connect locations. These are locations that we publish on our website. You can pick the location that's closest to where your data center is. And in each one of those locations, AWS will have a number of routers that we manage. And then you request a port on one of those routers, maybe 1 gig or 10 gigabits a second. And then you can establish physical connectivity to that port, either yourself or with the help of an AWS connectivity partner. So this is just your physical connection. On top of that, you now need to start creating your logical connectivity, so your virtual interfaces or VLANs on your side. So first, you can create a private virtual interface. That is an interface that gets you connectivity into your private environment, into the VPC. And for connectivity to outside of that VPC, to the publicly addressed services, you could use the public virtual interface. Now, if you're connecting to more than just a single VPC, and you want to use a single logical connection, for that, you can use AWS Direct Connect Gateway. In that case, you would create a single logical virtual interface, terminate it on the Direct Connect Gateway, that then can connect to up to 10 VPCs that live in the same region or in different regions across the world, except for China. OK, so if we now start connecting multiple VPCs, and we look at the time before we had TransGateway available, if we're connecting our VPCs back to on-premise using AWS site-to-site VPN, we would have to create a VPN per VPC. So each VPC would have its own VPN connection. If we had 100 VPCs, that means 100 VPN connections, actually 200 because there's 200 tunnels. If we're connecting back to on-premise using Direct Connect, then in that case, we could leverage Direct Connect Gateway and maybe have that single logical interface connecting to up to 10 VPCs. With TransGateway, we already know that TransGateway can help us aggregate the connectivity in a certain region, and we can connect up to 5,000 VPCs to a single TransGateway. But now it can also help us consolidate that connectivity back to on-premise. So instead of setting up a VPN tunnel to every single VPC, we can now have a single tunnel going to the TransGateway, and from there we can reach all the VPCs attached to it. If we're using Direct Connect, and this is currently only available in the US, we could use Direct Connect Gateway to connect a single logical interface to the Direct Connect Gateway and effectively to the TransGateway to reach all the VPCs. Now, from a routing point of view, it's still very simple. So all you need to do is now add an additional entry to tell the VPC how to get to the on-premise address range, and you just point it through the TransGateway. And the TransGateway is going to have its own entry for the connectivity back to on-premise. In this example, we're using a VPN, but it could be Direct Connect. So we've created a hybrid environment. We now have on-premise environment connected to AWS. But what about DNS? So typically, customers would have private domains, private zones deployed on-premise as well as on AWS, and they want to be able to resolve them no matter where they are. So for that, we have Route 53 Resolver service that allows you to create resolver endpoints in one of the VPCs connected to on-premise to be used for DNS forwarding. So you can do that resolution from on-premise to AWS and vice versa. And you can even create your own forwarding rules to specify which domains should stay on AWS and be resolved on AWS, and which ones should be forwarded back to your on-premise service. Okay, so it's been quite a busy year for networking, and we still have quite a few services to go through. So I'm going to touch on VPC sharing. I'm going to talk about VPC endpoints, and finally about Amazon Global Accelerator. So let's start with VPC sharing. And VPC sharing is changing the model of how you organize your VPCs. So before VPC sharing, when you created a VPC, it had to belong to an AWS account, which is a management boundary, and all the services you would deploy into that VPC would have to belong to the same account. With VPC sharing, we're changing that model. So you now have the concept of the owner account, and maybe this is an AWS account owned by your networking team or your infrastructure team. And they would build all the networking constructs. They would create the VPC, create the side-on-the-side range, create the subnets, set up all the routing, network access control lists, set up all the route tables and connectivity to other environments, exactly the same way as you would with a regular VPC, but it's controlled by that networking or infrastructure team. The big difference here is those subnets inside a VPC can be shared with other AWS accounts. So maybe now a web development team has their own AWS account, and they can deploy resources, EC2 instances, for example, into a subnet that's been shared with them. And they have full control over that resource, and they can create security groups around their own resource, but they cannot make any changes to the resources that were created by the owner of the VPC. So for example, they can't make updates to the routing table or change network access control lists. And you can share those subnets with multiple accounts. So maybe another account is maintaining a database and they're creating an RDS service. They could put it in another subnet, and maybe there's some application teams that are building their applications, deploying them into those subnets. None of those teams can touch each other's resources. They always manage their own resources. But from a networking point of view, if they open up the security groups, they can now communicate with each other. So why would you use VPC sharing? So first of all, you can save on your IPv4 addresses. If you're running out of IPv4 addresses and you can create one bigger VPC and put more resources into it, you're going to utilize your addresses more efficiently. And if you have less VPCs, it actually means less interconnectivity. You won't have to create as many peerings or TransGateway connections or connections back to on-premise. And you have that nice separation of duties where the owner creates the VPC and participants cannot change it. They can't accidentally on purpose add an internet gateway to establish internet connectivity, for example. And finally, everyone is still built for the resources they create. So, and if it so happens that the resources live in the same availability zone, then the traffic within the same availability zone is free of charge. Okay. So I mentioned earlier that we have these services that live outside of your VPC on the public AWS address space. And we know now that we can use Direct Connect, the public virtual interface, to access those resources from on-premise. But what about accessing them from within your VPC? you can do that through an internet gateway, but maybe you don't want to deploy an internet gateway to your VPC. So for that, we have different types of endpoints. And we'll start off with gateway endpoints. And these endpoints are used purely for S3 and DynamoDB, only for those two services. So here we have an example of a VPC communicating with an S3 bucket using the internet gateway. But in our scenario, we don't want to use an internet gateway. We don't want to use any public IP addresses, but we still want to be able to reach S3. We can establish a VPC gateway endpoint to S3 and then navigate all the traffic through an update in the routing table through that endpoint to privately communicate with S3 without any usage of public IP addresses. Another type of endpoint we have are interface endpoints. And these endpoints are now used by all the other services that are becoming available inside your VPC. So an example here is AWS Services API. So if you want to connect to that service, you can use an interface endpoint. And instead of doing any routing, we will make it look as if that service lives inside of your VPC, and it will use IP addresses from within your VPC range. So when your EC2 instances are connecting to that service, they would be connecting to a local IP address and behind the scenes privately transported to the actual service they want to communicate with. So this mechanism allows you to also override the public domain name for the service. So only inside your VPC, it will resolve to your private IP addresses. And a lot of customers and partners are using this for sharing their services themselves. So you can do it yourself as well. And the technology powering VPC endpoints, VPC interface endpoints, is private link. So we allow you to use that technology yourself to share your own services with thousands of other VPCs. So in this example, we have a service, maybe this is a HTTPS service, and you want to share that service with a lot of other VPCs, maybe some third parties. So you need to put it behind a network load balancer, and then make it available as an endpoint service, so that other VPCs can subscribe to that service and create endpoints representing your service in their VPCs. So again, they will be connecting to a local IP address representing your service and be transported to your service hosted in another VPC. And using private link allows us to only expose a specific service port that we're connecting to. So if it's HTTPS, it will be just 443. Connectivity is only allowed in one direction, so only consumers can connect to the service. The service provider VPC cannot connect to the consumer VPCs. And finally, in this scenario, you no longer need to care about IP addresses anymore. So those IP addresses in the VPCs can overlap, and you can still expose the service this way. Okay. Finally, a service that's focusing on something slightly different. So now we have an application on AWS that's already publicly facing, maybe in a region in Europe. And we have users from outside of that environment that want to connect publicly to our application. And we want to make sure that the experience for those users is as good as possible. So Amazon Global Accelerator is a network-based service that you deploy between your users on the internet and the application that's internet-facing, hosted on AWS, that allows you to optimize the experience for those users. And it can cover any type of application running on TCP or UDP. Why does it matter? So if we have an application that's facing the internet today, and we have users connecting from all around the world, they'll be traversing a lot of different networks, their ISP and some other carriers, and there's a potential for these paths to be impacted by some, let's call them internet weather conditions. So you don't control the end-to-end experience of that user. When you deploy a global accelerator, you're able to bring the traffic from your users onto the AWS backbone as close as possible to where your remote users are. And then from there, the traffic will use the uncongested managed AWS backbone to the actual service running in an AWS region. Okay, so we've covered quite a lot. We started with creating a VPC, and this could be a regular VPC or a shared VPC. We talked about how you can deploy endpoints to communicate with other services, AWS services as well as your own services. We talked about how you can connect your VPC to the internet and maybe optimize that experience using Global Accelerator. We talked about the different types of subnets, private subnet, public subnet, and using NAT gateway for allowing outbound access. And we talked about the different connectivity options, so connecting back to on-premise using Direct Connect or AWS site-to-site VPN, or connecting to other VPCs, whether using peering or using TransGateway. So that's a lot to cover, a lot that we covered. So if you have any questions, Perry and I will stay after the session. But you also can come over and chat with us at the AWS Village, where we have a networking stand. So if you have any networking questions, you can come over and chat with us. Yeah, and please make sure, thank you, and please make sure you fill out the survey. And remember, the exits are behind me.